Hi, in this video we will solve for the vibration, the modes of vibration of a metal bar by using Elmer Fem. And let's get started. Actually, before we get started, I would like to mention, if you want to run Salom on Arch Linux, I did a little script that helps you install it. You can find it in the description below, and the instruction on the repository will be, I think, will be pretty clear. Otherwise, Salom is pretty easy to install on Ubuntu. Just download the most relevant binary version. Also, another thing I would like to mention is that I will not be using Elmer as a native package on Arch Linux. The fact is that there isn't one, and there will be one package on the Arch user repository, but that is not building for me, and I'm having a very hard time in building the GUI for Elmer from source because some dependency issues. So I will be using the virtual machine that you can find here. So wiki. This is the Elmer repository. You will find the description for these, the link in the description for this as well. So just click on wiki, go to packaging, and as you can see, there are packages for Ubuntu. They are very easy to install. I did mention how to install Elmer on Ubuntu on my blog. It is very easy. But if you're not on Ubuntu, you can use a virtual machine. You can just download it from here, and it is very easy to get it working into VirtualBox. So let's go ahead. This is the virtual machine. So I just replicated our progress in here. So into the documents folder, I got our metal bar project folder with all of our files. You can see that the user in this virtual machine is Elmer user. So this is actually why I kept a very coarse mesh, so that we can solve it easily also on a virtual machine and learn how to use the software. I actually have a remote machine with Ubuntu somewhere else on which I can run bigger problems, and maybe I'll do. So I plan to show in these videos how to get a problem up and running, but maybe the heavy work will be done with finer meshes, maybe when needed, on other machines. And alright, I think we just can start now. So let's open the terminal. There's a handy icon in there, and let's open up the GUI for Elmer. Nice. So we can open our mesh. So let's navigate to where we put the mesh, and there it is, our UMV. We can open it up, and well, that sure looks like the mesh we did before. I'm just not gonna move this thing around the whole lot. I just not to have my poor computer explode while recording this. want to... Where's the compass? Oh, there it is. Just want to add a compass so that we understand how the thing is oriented. So view, compass. So the way we go ahead into setting up a solution for this physics problem is just by going down most of the items in here. So let's start from setup. This is the general setup for our finite element model, and we can see a couple of things. First, we will be saving the results of our simulation into a VTU file. We will use ParaView to look at that. We will be able to do so back into my Arch Linux box, my Arch Linux host. This is the solver input file that this GUI will be generating according to our setup. There's only one thing for this project that we need to take care of, and it is coordinate scaling. So if you remember, every time we defined the dimension of our bar, we did so in millimeters, but when we import the UMV file into Elmer will think that those are meters. So that's how we tell to Elmer to treat those dimensions as millimeters, so that we can apply. So now we're ready to define an equation. So it's going to be linear elasticity. Let's just change the name. So it isn't necessary to change the name. It could be anything. The name can literally be anything. It is a good practice to do because this is a multi-physics solver, so you could have many bodies, each one governed by a different equation. So this is not the case now. We only have one body. I don't know why it is called body 7. Maybe we can set that up somewhere in Salon. But we're going to use one equation, active, for just this body. And let's edit the solver setting. In fact, we just decided to have an equation governing this system, but we need also to solve the equation, so we need to set up the solver. And the first thing we will do is to click on Eigen Analysis. In very few words, this is how we instruct Elmer FEM to search for the modes of vibration. So we will be searching for resonance, frequencies, and the associated vibrations. Although in reality, Elmer will find the eigenvalues and the associated vibration, which is really the same thing. The eigenvalues are just the square of the angular frequency associated with the resonance frequency, and the eigenfunctions are just the vibration, the modal vibration themselves. We are gonna search just for the first 5 modes with the smallest frequency. Essentially, this is what we're gonna do, and I think we did all there is to do in here. Nothing to change in there. Looks good in here as well. Now our solver, our equation is linear. We will be using a linear material. We will assign a material to this metal bar later, and they will be aluminium, but isotropic linear model of aluminium. So the whole problem actually is linear, so we need no linear iteration. If we had to leave that at 20, the solver would just keep on giving us the same result 20 times. So let's just put it to 1. Now we go to linear system, and actually this kind of problem can be easily solved by a direct method with UMFPAC solver, and I'm just gonna set up an ILUT preconditioning. I came to this combination mainly by trial and error. We will maybe have a look when we get to more complex problems how you can figure out the best combination. Normally you can look at the equations governing the physics you're trying to solve for and figure out something, but maybe some refinement will need to be done by trial and error. So I think that's pretty much it. So we can do apply and OK. So I think now, yeah, our equation is ready. So as we mentioned, let's just make our metal bar to be of some generic aluminium. So by selecting aluminium in the model library, we just fill the parameters, also the linear elasticity parameter. So if you know a little bit of material physics, you know that we are really modeling this material as an isotropic material, and let's just apply this material to our body, and let's click OK. So we did mention that we need boundary conditions, so we could add a body force. It is a force that is applied to each volume of our domain, but we don't need it for this study. We are not gonna be able to apply an initial condition because our problem is an eigenvalue problem, not a time domain problem, and so we are really only required for this problem, for this model, to apply a boundary condition. So let's go ahead and create one. I think I want to make one of the faces, the base of our metal bar, to be fixed, which means that we want directly boundary condition. So condition applied on the field we're solving for, so on the displacement, which is the ultimate solution, and we say whatever boundary we apply this condition to, that stays still, it doesn't move. So the displacement from the position of rest is 0. Let's call this boundary condition fixed. So we can select the boundary to where we want to apply the boundary condition in there, but I like to do another thing, which is go here and do set boundary properties. So the boundary to where I want to apply the boundary condition is the bottom one. So we can see from the compass that this is the bottom one, so double click. And if we double click our boundary, we can see that we select it and it becomes red. So you remember when we were using Salom we created groups, one volume group and 6 faces group. So that's exactly what we are selecting here. We are selecting one of the faces group. This is how Elmer recognizes bodies and boundaries. So bodies are volume groups in the UMV mesh we prepare with Salam, and boundaries are faces groups in the UMV mesh we prepare with Salam. So we selected this one, and let's apply the fixed boundary condition we just defined. So and alright, so that's it. Let's go ahead and let's save the project. So now this is slightly misleading in Elmer. So you open up a dialog to save, and then it says open. The reason is that Elmer doesn't save one project file but a collection of files, and he wants us to give a target directory to where to save all the different files. So let's create it, and in our project folder I'm gonna create an Elmer folder. It can really be called anything, and it can be created anywhere in your file system. I just like to have one project folder for everything. And now we can click open. So if we go to our file manager, now we have in our project folder the Elmer folder, and in the Elmer folder all of our project file with our solver input file. And we can read the solver input file in here, and we can also edit in case we need to do so. And everything looks just like it is supposed to look, which is the way we set it up with the GUI. And there are cases in which not all the parameters are available, or not even all of the solvers are available through the GUI, and you may have to edit this file where you do more advanced things. But for the time being, this is just a very simple project that can be run completely through the GUI. So to solve, we can go ahead and click Start Solver. And it actually already finished, and the convergent history window we really don't have a plot to show because we only do one nonlinear iteration, covered the log, and yep, that's it. It is already done, and this is already part of the solution we're searching for. These are the first 5 smallest magnitude eigenvalues, and by smallest magnitude I mean the magnitude of the eigenvalue itself. And we will see in the next video about post-processing how to go from these numbers to the resonance frequencies. So what we found right now are the first 5 resonance frequencies, and in our VTU file that we exported, which is in here, right? No? Oh yeah, which is in here. There are also the modes of vibration of our bar. So I think we can call it a video and see you on the next one. Hi, before we go ahead and look at the results, I would like to point out a couple of additional things about our problem. So let's open up Elmer again. And let's load our project. Just open the directory. Okay, so if we solve the project again, cool, we can see our log file again, and we can actually save it, and let's do that so that we can use the log file later in our post-processing save. Now I think it would be interesting if we actually change the problem a little bit and look just at what happens. And so let's put 12 here, and now let's go to the bottom face again, and let's remove the boundary condition. So now we have no boundary conditions applied on the bar, which means that we are modeling a free bar. So will it work? And it looks like we didn't save, so let's save. And let's try it again. Okay, yeah, so it looks like that it worked, and of course we have 12 eigenvalues now, but you can see that the first 6 are very small. In fact, they are supposed to be 0, and the reason is that when a bar is free, the first modes of vibration will be just the bar moving along each one of the Cartesian directions as a wall thing, as a rigid thing, and rotating around these same directions. So we have as many zero frequency modes, so bar moving rigidly, as there are rigid body degrees of freedom. So these first 6 modes really are not interesting. They just reflect the fact that since the bar is free, it can move along each one of the directions and rotate around the same directions. So the modes we're interested in are actually these ones. But let's just go back to fixed, and let's just put it back to the file. Save again. And now we are in the same condition in which we left on the last video, but with the difference that we just saved our log file. We did that before, so we don't do that again. Okay, so in the next video we will be looking at the results.